All right, moving on, we're going to talk about kind of what's going on within the atom and like kind of the breakdown of what these subatomic particles kind of do. So most substances are not pure, right? It's not just purely hydrogen or purely oxygen. Most substances are made up of a combination of different elements altogether. So you have a molecule or you have a substance that's made of hydrogen and carbon and nitrogen all together. The important piece when making these different substances is not the protons like we talked about earlier, but the electrons. The electrons are the ones in control of determining how these different atoms are going to bond together. Electrons, we mentioned, are in a cloud, and so they're always moving. They don't sit still, they don't just hang out, but we do find them in particular shells. Now we've kind of just talked about a cloud as this kind of like indistinct area surrounding a nucleus of an atom, but we do find them with some certainty within certain levels or shells, right? And so let's look at some of these shells. So different shells can hold different numbers of electrons. So the closest shell, right, the one closest to nucleus, can only hold up to 2. Only 2 electrons can be really close to the nucleus. We go up one level to shell 2, we can hold up to 8. We go up another level to 3, we can hold 8 again. And then level 4, 18. We're not going really further than that. Again, we're simplifying things because if you do take something like a Gen Chem class, you'll see that there's a lot more levels. There's 7 of them, and it gets more complicated on how and where these electrons are found. But we're going to keep it relatively simple when talking about the different shells, with the first closest to the nucleus shell being holding 2, the second and third shells holding 8 respectively, like each, and then the fourth shell containing 18. All right, so here we are kind of looking at oxygen. So oxygen, right, is going to have 8 electrons. Remember, that's its atomic number is 8. So a standard oxygen atom is going to have 8 protons, neutrons, and electrons. But remember, we have 2 shells. So the first shell we're going to fill up with 2, which means the remaining 6 are in this outer shell. But that means we have 2 vacancies. So oxygen can hold up to 2 more electrons easily. So we fill up that first one, capacity of 2, and then any remaining electrons we fill up the next one. And if there's space available, that's going to help us determine what and how we're going to bond when it comes to binding with something else. Okay, so we look at the periodic table, and we kind of break down how many electrons can fit in each. Remember, we have this kind of funky shape. So we have these guys, hydrogen, helium up at the top by themselves, and then the rows get a little bit bigger until we get down towards the metals. So in this top row, we only have a first shell. We can fit up to 2 electrons, and that's it. Our second shell, we can fit up to 8. Third, up to 8. And then once we get down to that fourth shell, we can fit up to 18. Right? And then we get down to the sixth one, 32. 32. So we see how many electrons we can fit in those the outermost shells. It's a lot. We call the lowest energy shell, which is the one close to the nucleus, has to be filled first. So we can't necessarily put electrons in the outer shell just because we want to. Like that oxygen that had the 2 empty spots in the outer shell, we could not take the 2 electrons from the inner shell and put them in the outer shell necessarily. So we fill up the lowest energy ones, the ones closest to nucleus first, and then work our way out. That most outer shell with the vacancies means that our atom is unstable. It's going to want to react with something. And that it can do that by giving, taking, or sharing electrons. And we'll talk about those in just a little bit. If the outer shell is full, which we sometimes do call this outer shell the valence shell, so if you're using other resources, you may see that valence shell as another term. But if we have a full outer shell, then our atom is stable and we don't want to react. So things like the noble gases have a full outer electron shell. They don't really do anything. They don't want to react with anything. Right? Atoms want to get that full outer shell if they don't have it, and they will do whatever it takes to get that full outer shell. When we're talking about pure elements, the number of electrons is the number of protons, not necessarily neutrons, but is the number of protons and electrons are going to equal each other. We'll talk about a couple instances where they don't, but in general, when we're looking at a pure element, electrons and protons equal each other in terms of numbers. So let's go ahead and look at this stability. So here we have hydrogen, which it only has one shell, the lowest level shell, and it only has one electron, so there's one vacancy. Nitrogen, same kind of situation where the outer shell has some vacancies, 1, 2, 3. These two atoms, they're going to want to find electrons from somewhere else, whether they take them from someone else, whether they share them with someone else, whether they give them to someone else, doesn't really matter. But we want to accomplish a full outer shell somehow. Whereas helium and neon, like I mentioned, those noble gases, they're stable. They don't have any empty spots. There's no empty slots in either of these. And so because there's no vacancies, they're going to kind of just hang out by themselves. They don't need anyone. Right, so like I mentioned, that outer shell, also called the valence shell, the number of electrons that we find there can kind of help tell us how this atom is going to react or how it's going to behave. Right? So if we look at the organization again, we group things together based on similar properties, namely how many valence electrons they have. So everyone in group 1 has 1 electron in their outer shell, and then group 2 has 2, group 17 has 1, 15 has 3. Like those are just, you don't have to memorize these numbers. I don't expect you to memorize the periodic table, but just understand kind of what these things mean. Now, because we want to fill that outer shell, or we want to have an outer shell that has that full shell of either 2 or 8 or 18 or 36, however many, sometimes we can give or take those electrons that we have. When we do that, we become ions, where the protons and electrons don't match up in numbers anymore. So we call that process ionization, and ions can lose or gain up to 3 electrons. Right? Now remember, we cannot lose or gain protons. We're only talking about electrons when we're talking about ions. And so we'll see this little symbol like a plus or a minus sign to show us the charge based on how many electrons we have gained or lost. So when we're just talking about atoms, protons and electrons, their numbers equal each other. But with ions, we don't have to have the same number of protons and electrons. They can be different. If we're positively charged, meaning we're a cation, we have more protons and electrons. So we have lost some electrons. We've given some electrons away to be positively charged. Negatively charged ions, also known as anions, have more electrons compared to their protons. Right? And so we show that with a negative sign. And if you think about it, it makes sense. In a positively charged ion, we've given away electrons which carry a negative charge. So if we give away something negative, now there's more positively charged components than negative, so the positive outweighs the negative. In the negatively charged ions, there's more electrons than protons. We've gained some electrons, and so there's more negatively charged pieces compared to the positively charged, so we have a negative charge overall. So you think of like for every electron, proton, that they're going to cancel each other out, and so whoever you have more of in the end is going to represent the charge. So let's go ahead and look at this process here. So here we have sodium and chlorine. Sodium has 1 electron in its outer shell. So the easiest way to get a full shell is to give that 1 away and just go down a level. So otherwise we would have to get 7 electrons from somewhere, and that's really hard. It's hard to get 7 electrons, but it's easy to give away 1. So sodium was going to give this electron away, and it's going to give it to chlorine, which has 7 electrons in its valence shell and only 1 vacancy. So by giving that electron to chlorine, sodium satisfies this outer shell, and chlorine has the donation to fill in its outer shell. So everyone's happy. But if we look at the charge, we've given away a negatively charged component, so our net charge is positive because there's more protons than there are electrons. Protons outweigh the electrons now. In the chlorine, which now we call a chloride ion, we've gained a negatively charged piece. So electrons are going to outnumber the protons. And since electrons, which are negatively charged, outweigh the protons, we end up with a negative charge.